Hello. This is day three. So I covered like three chapters in 2 days. So today is the third day, and we'll try to finish this important topic, ownership. I think this is one of the main important aspect in Rust, which differentiates it from the other languages. So let's start that. When we wanted to write code, we'll move to VS Code. So until then, we keep going. So ownership is Rust's most unique feature and has deep implications in the rest of the languages. It enables Rust to make memory safety guarantees without needing a garbage collector. So it's important to understand how ownership works. In this chapter, we'll talk about ownership as well as several related borrowing, slices, and how Rust stays data out of the memory. So ownership is a set of rules that govern Rust program manages memory. All programs have to manage the way they use computer's memory while running. Some languages have garbage collection, regularly looks for no longer used memory as the program runs. Other languages, programmer must explicitly, This is like C family of languages. Uh, so I have tried C long back while I started learning the programming. So I kind of get this. So then there are other type of categories which is actually garbage collected, which Go, C Sharp and JavaScript, which I have used, belongs to that category. So what they are essentially claiming is this is neither that nor this. This has a different approach. Memory is managed through a system of ownership with a set of rules in that compiler checks. If any of the rules are violated, the program won't compile. None of the features of ownership will slow down your program while it's running because it's compile time, right? So that makes sense, and it's interesting as well. Because ownership is a new concept for many programmers, it does take some time to get used to it. The good news is that the more experience you become with Rust and the rules of ownership system, the easier you will find it naturally develop code that is safe and efficient. Keep at it. When you understand ownership, you will have a solid foundation of understanding the features that make Rust unique. In this chapter, you will learn ownership by working through some examples that focus on a very common data structure, strings. I think we didn't, we only saw the like primitive data types, that we didn't go into much of collections or any stuff, I think, yet. So that's the reason they are focusing only on strings for this particular example, to keep only ownership intact, not getting lost in terms of other things. The stack and the heap. Many programming languages do not require you to think about stack and heap very often because, but in systems programming language like Rust, whether a value is on stack or heap affects how the language behaves and why you have to make certain decisions. Parts of ownership will be described in relations to stack and heap later in this chapter. So here is a brief explanation and preparation both. I think I know already like what is stack, what goes there and what goes into heap. I'll just quickly skim through this just in case anything is, am I missing? Yes. Yeah, whenever we have kind of a reference type, we put the pointer to the stack and the actual value presents in the memory address where it is pointing in the stack. I think that is what it is they're trying to say. Yeah, accessing data in heap is generally slower because we need to keep following the pointer to get the value, not like direct read from the stack. Right, it's much slower. It's pushed back, keeping track of what parts of the code, minimizing the amount of duplicate data on the heap, cleaning unused data on the heap so that you do not run out of space on all problems that ownership addresses. Once you understand ownership, you won't need to think about stack and heap very often. Yeah, okay. I think this is just a refresher to these concepts. There is nothing that's a fundamental which I already know. So though no need to worry about that. Let's come back to ownership rules. First, let's take a look at ownership rules. Keep these rules in mind as we work through the examples that illustrates them. Each value in Rust has a owner. Therefore, there can be only one owner at a time. When owner goes out of the scope, the value will be dropped. Okay. Yeah, this makes sense because every value somebody should own it. That's a strict enforcement they're trying to make. Only one owner can claim for a particular value at one time. Okay. Yeah, this is fine. I think when we see examples, then this will make more sense and why it is in certain way and how it is helpful we can get, I believe. Variable scope. Now we are past the basic Rust syntax. We won't include that, is fine, fairly fine. So if you're following along, make sure you put the examples inside main function. Yeah, I will do that as a first example of ownership. We'll look at the scope of some variables. A scope is the range within a program for which an item is valid. Take the following variable yes. Okay, s is valid here, valid from this point. Yeah, in other words, there are two important points in time here. Okay, when s comes into scope, it is valid. It remains valid until it goes out of the scope. At this point, the relationship between the scope and when variables are valid is similar to that in other programming languages. Yeah, okay. Now we'll build on top of this understanding by introducing the string type. Okay, fine. To illustrate the rules of the ownership, we need a data type that is more complex than those we have covered in data types in chapter 3. The types covered previously are of a known size, can be stored on a stack and popped up the stack when their scope is over, and can be quickly trivially copied to make new independent instance. Okay, yeah, that is correct. Okay, so the only difference in this string, this can be of varied sizes. We'll concentrate on the parts of the string that relate to ownership. These aspects also apply to another okay, that's fine. We have already seen string literals where a string value is hard-coded into our program. String literals are convenient, but they aren't suitable for every situation in which we wanted to use. Yeah, that's correct. Because when we have a situation that we wanted to get dynamic inputs, maybe parsing something from a text file or reading inputs from user, I think what we have done in the guess game in the first example, in those type of scenarios, like command line input is a very common thing when we build CLI applications. We need to get output from the user, so that length is varied. So for that we need a this type of data type, right? Mutable strings basically. Yeah. Oops, no, not the compile time. Yes, the double colon namespace from particular. Okay. Yeah, the kind of string, this kind of string can be mutated. Yes, push string. Yes, okay. So what's the difference here? Why string be mutated but literals cannot? The difference is how the, okay, well, I think one goes into the stack and the other goes into the heap, right? Let's see. Content, we know at compile time, we know what is the value. So yes, this is in the final. Yes, this is why string literals are fast and efficient, but these properties only come from the string literals immutability. Unfortunately, we can put a blob of memory into, yeah, okay, within the string type. In order to support mutable growable piece of text, we need to allocate an amount of memory on the heap unknown at the compile time to hold the contents. This means the memory must be requested from the memory allocator at the runtime. We need a way of returning this memory to the allocator when we are done with our string. That first part is done by us. Its implementation requests the memory it needs. This is pretty much universal, yes. However, The second part is different. In languages, garbage collector keeps track of and cleans up the memory. Yeah, so here that is what we are doing it slightly differently. Rust, yeah, memory is automatically returned once the variable that owns it goes out of the scope. Yes, there is a natural point at which we can return the memory or string needs to the allocator. When s goes out of scope, when a variable goes out of scope, Rust calls a special function for us. This is called drop. It's where the author of string can put the code to return the memory. Rust calls drop automatically at the closing curly bracket. This pattern has profound impact on the way Rust code is written. It may seem simple right now, but the behavior of the code can be unexpected in more complicated scenarios. Situations when we have to have multiple variables use the data we have allocated on the heap. Let's explore some of those situations now. Okay, this is I think copy because it's a fixed length type and it's on stack. It's a value type, so this gets copied. Actual value gets copied, but here we are actually copying the references. Yeah, that's what they're saying. Yes, this is common. No need to completely not need to copy the data. Yeah, because copying the data involves like going through the entire heap, actually copying the data, which is time consuming if it is like 1 million items in an array or a so big string. Just copying the reference address and the length and capacity is like cheap. So that's what it does by default. Copying the heap data as well. Yes, it could be very expensive. Yeah, that's what they're trying to say. So earlier we said when variable goes out of scope, Rust automatically calls drop function and cleans up the heap memory for that variable. So same location. This is a problem when S2 and S1 goes out of scope. They both trying to. This is a double free error. It's one of the most. It's one of the memory safety bugs which we mentioned previously. Freeing the memory. Yes. To ensure memory safety after line, Rust consider S1 is no longer okay. Yeah, that's nice. If you heard the term shallow copy, deep copy while working with other languages, the concept of copying the pointer length capacity without copying sounds like making a shallow copy. But because Rust also invalidates the first variable, instead of being called a shallow copy, it's known as move. Okay, yeah, technically that's what is happening. In this example, we would say S1 has moved to S2. What actually happened? Yeah, this goes up because this goes out of the scope and this responsibility goes to S2. Okay, this solves our problem. The dangling pointer problem is gone. In addition, there is a design choice that's implied by this. Rust will never automatically create deep copy. Okay, whenever we do this, yeah, that's fine. Scope and assignment. The inverse of this is true for the relationship between scoping, ownership, and memory being freed via drop function as well. When you assign a completely new value to an existing variable, Rust will call drop and free the original value's memory immediately. Okay. This is mutable, so we are actually assigning, but what's happening here? It needs to clear this hello and it needs to do this. So this whatever is there in like where this hello is stored in the heap should be destroyed, and we need to put this ahoy into the heap. I think that's what it's doing. We initially declared a variable s and then we immediately create a new string with the value. Yeah, yes, the original string immediately goes out of the scope. Rust will call drop function. Yes, variables and data interacting with clone also will behave the same way, I think, right? So this is there and it needs to again allocate and copy whatever it's there from the heap from that memory and to put it in the new memory and then assign those things to the stack. That's what is happening here. It's a common feature in many, as we have seen. Yes. Okay. Stack only data copy. There is another wrinkle we haven't talked about it. Okay. What's that? This code using integers part of this works and is valid. But here, because this copying is cheap and it is just the fixed length value, so this is copied to x and this is x is copied to y. So the actual value like resides in y, it resides in x. So this doesn't have a problem. This both are not like pointing to some address. This is actual value in a different variables. So that is fine. So what they're saying, the reason says compile time, yeah, stored entirely on the stack. So yes, yes, Rust has a special annotation called copy trait that we can place on the type. Okay, I think all the value types like integers, numbers, and string literals, those sort of stuff has this copy trait, which means that acts when we do like this variable, like this kind of copy, the actual value gets copied to this new variable. But whereas in those type of reference variables, reference types, so which means that string and other lists collections will not have this copy trait by default, right? List won't annotate, yeah. So if type or any of its parts has implemented the drop trait. So it is either we can implement copy trait or we can implement drop trait. If it is drop trait, it should be with those like reference type variables. So if copy, then it is basically the fixed stack allocated data types, right? So only one, that's also like constraint with the compiler, I believe. So what types implement? Yeah, that's what we kind of understood already. Yes. Okay, so tuples, if they only contain types that also implement copy, for example, then implements copy, but this does not. Okay. What is this? So if they contain only, okay. For example, if a tuple contains only like fixed size types, which is both are integer, then this whole tuple also can be like copied. Whole tuple value also can be copied because copy trait is there. If one of it is differ, then I think it won't have this copy trait. So it will be like again go into the drop trait with reference types. I think that's what they meant. Ownership and functions. The mechanics of passing a value to a function are similar to those when assigning a value to a variable. Passing a variable to a function will move or copy just as the assignment does. Okay, list 4 has an example with some annotations showing where variable goes into and out of scope. Okay, I think let's start writing the code here. Day 3 cargo. Let's create ownership. Yes, let's do minimize this. Okay. Okay, so let s is equal to from hello and then let's print line yes. This is fine. So let's collapse this. Okay, so now oh, I think the moment I collapsed like few things, I pushed down. Okay, where are we? This I covered. This also I covered. Ownership and functions. Yeah, I think we're here. Okay, so S comes into scope. Take ownership. S values move into the function and is no longer valid here. So here some string goes out of scope and drop is called. The backing memory is freed. Makes copy. Okay, here some integer goes out of scope, nothing special happens. Yes, that is correct. Because actual copy happened. So let's just take ownership and then some string. Now let's put some string. String. So now let's this happens. Now what happens now, because we passed it to here, then this goes out of valid, right? Borrowed of the moved value. Borrow of the moved value because we moved. Okay. So now in order to use this, I think we need to again send back this and then again let ts equal to assign this. Okay, got it. Yeah, this is fine. Try to use okay return value and scope. Okay, I think that's what they are also saying. 3 string give ownership. Oh, they okay. Takes and gives. Okay, let us also write like this: take and gives ownership. Takes and gives ownership. Okay, gives ownership is something we create and we pass this, and now yes, one is there. Okay, now what are this? Some string comes into scope. Some string is written and moves out to the calling function. Yeah. Okay. Yeah, I think then required. It's fine. We understood. This is takes and gives back. Yeah. Okay. The ownership of the variable follows the same pattern every time. Assigning a value to another variable moves it. When a variable that includes the data on the heap goes out of the scope, the value will be cleaned up by the drop unless the ownership of the data has been moved to another variable. While this works, taking ownership and returning ownership with every function is a bit tedious. What if we want to let a function to use a value but not take ownership? Yeah, because that's what I tried initially here. So I don't want to do this. I just wanted to send this to this function, but at the same time I want to use this here, which means what is the option? That's what we are going to see, I think, right? Okay. The ownership. Okay. While this works, yeah. In addition to this, let Rust does allow return multiple values using tuple. But what is that? But this is too much ceremony and a lot of work for a concept should be common. Luckily, okay, references. Okay. references and borrowing. The issue with the tuple code. Okay, let's go. Okay. Let me also write this. Let yes equal to this works, right? Yes, this is one set. And now calculate. Let's say we get string and then we return string comma use size. Let length equal to s length. Okay, s comma length. Okay, now let's do this. S2 comma length equal to calculate s. Now print ln s2 comma length. Okay, just run cargo go run. Yeah, see this is fine. So now okay, this returns the okay, but this is too much ceremony. Yeah, that's correct. Now the issue with this tuple code is that we have to return the string to the calling function so that we can still use the string. I think this is just a same example, but that's fine. So let's just yeah, let me put some different value to have the same. Yes, calculate. Yes, 2. Okay, yeah, this is example 2. Okay, yeah. We need to pass, so that's what they're saying. So now the solution to that is passing references. I think that is what is this. So when we pass this, then we can still use this. Okay, first notice all the tuple code in this variable declaration function is gone. Second, note the okay, so one more thing is, what is this u size? The size of this primitive is how many bytes it take to reference any location in the memory. Okay, but why can't it be like just a u that me okay. Pointer sized unsigned integer? What is that? Because your machine is 64-bit. Okay, when to use? Indexing memory slash collections. Okay, but why that exist? That exist as a type rather than just using already available U32 or U64. Because Rust needs one integer type, that means big enough to address memory on this machine. That is what usize is. It is not mainly a number type. It is a memory index slash size type. Why not always U32 on a 64? Hmm. Okay. Okay. I think so. If we use this is kind of a generic type. So based on the machine, it just allocates either it's 32 or 64. So we don't need to take care of it based on the allocation. So I think that's the reason this distinct type exists. Fine. Uh, yeah. So now let's come back to this reference type. So if I do this like function calculate reference, so I need yeah, that's trivial because I don't need to like pass. Oh, yes, dot length. This should be fine. Oh, so yes, yeah. So because we are passing reference, or like let's say now, let me introduce some new thing like a city from to. So now if I do calculate reference city, then again if I do print line city equal to city, you should, what's the problem? Okay, I should, yeah, got it. This is fine because we are passing reference, so which means we are not transferring the ownership to this function. We are keeping the ownership within this main scope, that is from this line. So that's why we are able to, yeah, clear. Okay. The opposite of referencing by using this is dereferencing, which is accomplished with the dereference operator. We'll see some uses of dereference operator in chapter 8 and discuss details of dereferencing in chapter 15. Okay, yeah, for now let's go in the same order. Let's not get too much confused. So yeah, this is so far this is good. Does not own it because reference does not own it. The value it points to will not be dropped when the reference stops being used. Yeah. So if it is dropped, then like we won't see the city here. So that's the whole point of passing this reference. Okay. But because yes does not have ownership, it refers to the string dropped. Okay, fine. So what happened if we try to modify something we were borrowing? Okay, it won't allow because it's not a mutable reference. If we wanted to do that, then we need to do this. This is should be okay. So let I'm running out of okay, let me just put place equal to string dot from my place. They should be mutable, right? So this should be mutable and then change place. So and mutable place. Now change place. Function change place. So now this should be place mutable. Should I write? Yeah, mutable mutable, not this string. Yes, so now we can do this, and I can str new place. So now if we do the print line, new place equal to new, what happened? Oh, sorry, new place. Yes, let's do cargo run. Yeah, it changed because this is a mutable reference, right? Yes. If it, okay, what is this? Mutable reference have one big restriction. If you have mutable reference to a value, you can have no other references to that value. Okay, this code attempts to create two mutable references, it will fail. Okay, why? The error says this code is invalid because we cannot borrow s as a mutable more than once at a time. The first mutable borrow is in R1 and must last until it is used. But between the creation of that mutable reference and its usage, we try to create another mutable reference R2 that borrows the same data as R1. Okay. The restriction preventing multiple mutable references to the same data at the same time allows for the mutation, but in a very controlled fashion. It is something that the benefit of this is to have data races. A data race is similar to a race condition and happens when these three behaviors occur. Two or more pointers access the same data at the same time. At least one of the pointer is being used to write the data. There is no mechanism being used to synchronize access to the data. Okay, data races can cause undefined behavior and can be difficult to diagnose and fix when you are trying to track down at runtime. Rust prevents this problem by refusing. Okay. But okay, yeah, okay. I think if R1 is not being used, if we try to use R1 after this R2, but before that, if we clear R2 completely, then R1 also will be cleared, but our assumption will be wrong. Like it goes out of sync. So that's why they are not allowing. I mean, okay, because no problem, because this is not a mutable reference. But if it is like both are mutable reference, then it's kind of an issue. Okay. We also cannot have a mutable references while we have an immutable reference on the same value. Hmm. Oh, even this is also. Hmm. This is also not possible. Two mutable references is also not possible without one being used and one. Okay. One reference and one mutable reference. That is also restricted. Okay. The scope of immutable references R1 and R2 at the end of where they last used to, because which is before mutable reference R3 is created, these scopes don't overlap, so the code is allowed. The compiler can tell the difference. Okay, even though borrowing errors may be frustrating at times, remember it's Rust compiler pointing out a big potential bug. Okay. Yeah. So ideally, this is not a, like, why do we need to create back to back with one not being used? So that's correct. I mean, so the same example, like if this is cleared and we still believe that this has value, that creates a problem. So they stop that from being happen in the compiler level itself. So that is good. Also, in general, I tend to create the variables like close to the place where it is used. I don't know, as a general habit, but here we are forced to do that. The language forces us to do that. Okay, dangling references in languages which pointers, it is easy to error. Yeah. Okay, so now this is the same problem. Okay, reference to nothing. Because if we pass the reference, this s, that drop being called after this, like, this variable goes out of scope, that is this, so it will be called, but ampersand of s will point to nothing, so that's why they are like stopped. See, if we wanted to do this, then we should do only yes. Let's do only yes. Yeah. So the rules of references, let's recap what we have discussed. Okay, at any given runtime, you can either have one mutable reference or any number of immutable references. References must always be valid. I think this point, let me just take a note. This is a main important bulletin. Right. Yeah. That's fine. We look at different kind of references, slices. Okay. Let's see, where are we? I think slices is the last. Okay. Let's collapse this. Yeah. Then let's write Daniel. So let s equal to string dot from Daniel value. Yeah, just give some random. So if we do this, what's the, oh, I'm making, okay. It is correct, right? Like, what is happening? So, okay. So what is this error? I think that is what is happening right now. Consider using, okay, I think this is what it's like trying to prevent even from this. Okay, yeah, this is, we just comment it. Let's do this. So now this should be fine. So this way we can just pass. That's the thing. Okay. Slice let you reference a contiguous sequence of elements in a collection. A slice is a kind of reference, so it does not have ownership. Okay, here is a small programming problem. Write a function that takes a string of words separated by spaces, return the first word it finds in that string. If the function doesn't find a space in the string, the whole string must be one word. Yeah, this is fine. First word. I think this. Did we write any for loop so far. Okay, there is no for loop. Okay, that's fine. Yeah. So let's write our first word. What we need to pass here is the string and we need to pass the string. We need to send what use size. The way they are doing is to find out the starting length, right? Yeah, where the space is there. That's what they're trying to find out. Let's say bytes is equal to my string has bytes. Now for I comma the item in bytes enumerate if what is it, if item equal to byte of space, then what happens? This is syntax, right? So return I, otherwise s dot, oh, not s, we have my string dot length. Okay, so now let's call this method result equal to first word of hello space world print line first word equal to result. Okay, so now what's the problem? Because it's okay, we cannot put string literal. Okay, so let sentence equal to string from. Okay, so now let's do cargo run. So now what's happening? First word equal to 5. It just like gave the length where to split. So from that we can split. So that's what they're saying. It is okay. Let mutable string equal to hello world first. But why it should be mutable? I don't need, like, why is it mutable? Oh, okay, because they're operating clear here. Okay, okay. Okay, so if let me do s dot clear, now it will throw an error because okay. Now what's the problem? Variable does not need to be mutable. Why? What's the issue here? Cannot borrow. The program compiles without any error, but they're saying it compiles. Oh, my bad. Yeah. So now this is compiling without any error. But the problem is, see, the first word, this length, it's showing it as 5, but we actually cleared it. So which means this is kind of not a correct answer. So that is what they're saying. No longer has the content. Yeah. Compiles without any error and would. So if you used word after calling clear. Okay. Having to worry about the index getting out of sync with the data. So now we are tracking starting and ending index. So we have even more values that were calculated from the particular state but aren't tied to the state at all. Okay, so what they're saying is slices would fix this, but how? A string slice is a reference to a contiguous sequence of elements of a string, and it looks like this. Okay. A world pointer is actually pointing to 6 and length is 5. Okay, name value pointer length. Okay, contiguous sequence of elements of a string. Reference to contiguous sequence of elements. Let me add this as a bulletin. Yeah, so that's fine. Rather than a reference to entire string, hello is the reference to a portion of the string. Yeah, that is the slice. Okay, understood with range syntax. If this means from the starting to, okay, I think that should be fine. Yeah, this I think when we are using, we'll get used to it. So that is fine. Conceptually, it is a reference type. It is also a reference type. That's what they're saying. It's a contiguous sequence of elements. Okay, but how does it solve this problem? So what is this? So now, see here, what are we doing? Okay, 0 to, we are returning a slice, which means we are returning the, so this, what is this? This is this. I think I already got this confusion. It's like time to clear this. This is this. Both reference to the text, but they are not the same level of abstraction. Think it like this. Okay, from okay. String name. String is the owned growable string type. Is reference to the whole string object. This means give me a borrowed string. Okay. But string str is a string slice. This means give me borrowed view of some u. Why are they mixing this with that? Okay, I think this is part of a string, but what's the difference? What's the difference? Okay, the text come from owned literal shan dev of literal. So is str is more flexible. Best rule. Prefer this. Borrowed text view. Didn't get it. Why it should exist? I think something is not clear for me. Is this because it's not all text? All text in Rust is a string. Oh, the reason this exists is because not all text in Rust is a string. String is only one kind of text storage. Rust has many places where text can live. One is this. Okay, text stored on the heap, only a part of the text. Oh, okay. Stored inside the program. Okay, this is literal, stored inside the program memory. This is on the heap, only only part of the text. Okay, part of the text, then where it is stored. This is also stored in heap or, okay, let's read through the common type. Think of string as a box. Okay, memory wise splitted pointer. Okay, pointer length capacity. You are borrowing the actual text view is basically pointer to the text and length. No capacity, no just a view. Okay, this is a good. I think this is what the document also has. I think, right? I couldn't. Okay, yeah. See, it only has pointer and length. Okay, I think that. Let me put another bullet point here. So this will have pointer and length, no capacity, right? Now this will have pointer, length and capacity. So basically this is just a view of a text from string slice. Yeah. Okay, yeah, I think that's what they're trying to say. So there are three types of string. One is this literal, other one is this growable string. Yeah, that also will put string types. What are the types? Like literal, growable string, portion of a string, portion of a string view. Yeah, I think that's it. These are the three things. Better to read. Yeah, good. Okay, so this is clear. Now let's come back to how literals would fix the error. That's our problem, right? So now if I wanted to, okay, where is the first word? Yeah, so F1 first word with slice. So now this will be instead of returning a size, now we are returning str, right? Slice. So yes, here my string, I think let bytes, okay, bytes equal to my string as bytes for in bytes dot getter dot enumerate. So here what we will do is we will get index and then we'll get a reference item. Now if item equal to top space, so we will return what we will return. We will return a slice, which means we should go into S and then from 0 to where is that index? Here that we will return, or otherwise here what we will return, string of S is written from start to end. Now this is what is a problem, because my string I just okay here also my string. Yeah, so now instead of this, let's say let mute slice equal to string from Shyam. Let result equal to this slice slice dot clear print line slice. Okay. Now what's happening? Yes, sir. Result. Okay. I will not call slice. What should I? Yes, we want just result, right? What? Okay. Now what's happening? Cannot borrow slice as a mutable because it is also borrowed as immutable. Okay, that's what they are saying. This is protecting. Yeah. So we have a mutable reference slice here. We actually pass that to this method. Okay, so because this mutable borrowing is still alive, it is not allowing it to whatever it's throwing. Cannot borrow slice as mutable because it is also borrowed as immutable. Mutable borrow occurs here. So what they are saying here also, the first word, immutable borrow occurs here. Yeah, here we are borrowing. Mutable borrow occurs here. Just put this just for this occurs here, right? Here mutable borrow occurs. That's why only one can occur. That's we have already written, right? At any given point of time, you can either have one mutable reference or number of immutable references. But here what's happening? Number of immutable references, but here we are at, oh no, that is different. Sorry, this is a different thing. Okay, so let me read. Immutable borrow occurs here, mutable borrow occurs here, immutable borrow later used here. Yes, immutable borrow later used here. So this is preventing it. The same thing here it didn't prevent. Why? Because recall from borrowing rules, if we have an immutable reference to something, we cannot also take a mutable reference. I have written this. I think this, what does this mean? You can either have one mutable reference or any number of immutable reference. So now which is immutable reference and which is mutable reference? So this is okay. This is immutable. This is mutable because we are actually clearing it. Here we are not clearing it. So that is correct. This is a statement. It's little tough to get it at first shot. Okay, understand. So now if I move this here, then everything should be fine because there is only one immutable borrowing and that we have used it here and there is no scope beyond this. So even if we clear, then there is no problem. So compiler is ensuring it. So fine, that's correct. So let me just like this whole thing, or let's do this, and if we move this line before print line, then we will have an error since the borrowing rules are violated. Yeah, understand. Okay, string literals as slices. String literals as, okay. Recall that we have talked about string. I think this is fine, right? Yeah. This is fine. String literals as slices. Recall that we have talked about string literals being stored inside the binary. Now that we know about slices, we can properly understand string literals. Okay. The type of S here is str. It's a slice pointing to that specific point of the binary. This is also why string literals are immutable. Str is an immutable reference. Okay. Kind of didn't get it still. Type, okay. It is a slice pointing to that specific point of the binary. This is also why. Okay. So, slice pointing to a specific pointer. Okay, fine. So this we know. I mean, this denotes it can't grow. It will only have pointer and length. So that's what they try to denote it here. In the binary, this will only be there. That's why this is immutable, because there is no like capacity. So there is no capacity. Yes. String slices as parameters. Knowing that you can take slices of literals and string values leads us to one more improvement on the first word, that it's signature. Okay, what is that? Oh, a more experienced trustees would write the signature as shown. Okay, because it allows the same function to use both str values and str values. If we have a string slice, we can pass that directly. If we have string, we can pass a slice of string or reference to the string. This flexibility takes advantage of deref coefficients, a feature that we'll cover here. Defining the function to take a string slice instead of a reference to string makes our API more general and useful without losing any functionality. I think this I didn't get. So if we have only this, oh, got it, got it. I think last time also somewhere I struggled. So if this is there, then I cannot pass this like string literal, right? I cannot pass this hello, hi. This will create a problem. But if I have this, then everything is fine, isn't it? Yes. Yeah, okay. So here, let's write this. Won't allow string literals. String literals are, I mean, both are same. I think I'll just put slice, right? So example, mobile. So this is not allowed. Yes. Yeah. Other slices, strings. Okay, string slices, as you might imagine, are more specific to string, but there are some more general slice types too. Okay, here is this. Consider this array. Okay. I think string slice, array slice. So which means what's okay, that we'll see later as they are saying in chapter 8. Okay. The concepts of ownership, borrowing, and slices ensure memory safety in Rust programs at compile time. The Rust language gives you control over the memory usage in the same way as other systems programming languages. But having the owner of data automatically clean up the data when the owner goes out of the scope means you do not have to write and debug extra code to get this control. Ownership affects how a lot of other parts of Rust work. So we'll talk about these concepts further throughout the rest of the book. Let's move on to chapter 5 and look at grouping the pieces of data together. Yeah, I think we'll stop here. I will run through this one more time because this is a lot of things we have covered today. So yeah, we'll stop here and we'll continue from chapter 5 tomorrow. I'll just glance it through this chapter completely one more time, just quickly, so that it gets stick in the head. So yeah, that's it for today, and we'll start chapter 5 tomorrow.